Hi, welcome back. So we will continue to look into chapter 15 today. Today we will talk about heat engines and the ideal or perfect heat engines called Carnot engines, and then also more application of heat engines in heat pumps, refrigerator, and or AC, etc. Okay, so let's get started with a quick review what we learned last time, because the topics last time and today's are closely related. So last time we talked about the first law of thermodynamics, which is basically conservation of energy. So the internal energy change of the system, delta U is equal to, it comes in two forms, heat added into the system and then the work done by the system. So delta U equals to Q minus W. Okay. Sometimes you might have multiple process going on at the same time, heat goes out, and at the same time heat goes in, work done to the outside, and then also the outside doing work to the system as well. So then you have to combine those. We talk about the application of the first law, which is a heat engine. So the heat engine will take in the heat and then convert partial part of the heat into work, and then the remainder of the heat will be discarded into the environment. So Q in is the heat takes in and then convert into work. W here, excess heat will come out. Okay. Um, and then we also talk about some simple thermal processes. So these are ideal processes. Isobaric specifically, so there are four of them. Isobaric, which means constant pressure, pressure is not changing. Isochloric, which means volume is not changing. Isothermal means temperature is not changing. And adiabatic, that means no heat transfer in or out of the system. For these four processes, the work done during the isobaric process that is equal to the pressure, which is a constant, times the change in volume. And for isochloric, because changing in volume is equal to zero, so the work done will be equal to zero. Isothermal, because temperature is not changing, so then internal energy is not changing, so then work equal to the heat. For adiabatic process, no heat transfer, so then heat equal to zero, Q equal to zero. All right, so let's take a look on the engine here. So naturally, this is a makeup engine. It takes in heat from a higher source. We call it higher temperature reservoir, and then convert part of work into part of heat into work. This is called the mechanical work that is converting from heat, and then excess heat dumped. Okay, so this process because this process is possible because that in natural heat transfer occurs from higher temperature object to a lower temperature object. Okay, so this natural occurrence is called it's in the second law of thermodynamics. And this is the one of the expression of the second law. Second law comes with different expression, but fundamentally they are the same thing. We actually had took a expression earlier last time, which says you cannot convert all the heat into all the work. Okay, so heat cannot be turned into the work without having an excess heat. Okay, last time. So that's also another expression for the second law of thermodynamics, but this is the first expression. Okay. All right. So this is again just a cyclic process for a heat engine that you have in your car, most likely if you're still using a fuel car, fuel powered car. So fuel comes in mixture with the air, and then so you ignite it. So when they come in, first they become compressed, and then the mixture will be ignited, so generate a lot of heat. Okay, so then it expand the volume of this heat gas system here. It pushes this piston, which will be doing the mechanical work, and then after mechanical work is done, the piston will be compressed back to the original position with exhausted heat, excess heat going out. Okay, so that's a fully cycle, and then the cycle starts from here, takes in air and fuel, and compressed further and then ignite, and then does the work, and then piston goes back to the original position. Okay. All right. So this diagram on the right is just a simple representation of the whole cycle, where the heat takes in, the engine takes in heat and convert heat, part of heat into mechanical work, and then excess heat will be dumped out. The whole process can also be represented by a PV diagram, which in this case, the heat takes in from here, this process from B to C, where volume is not changing, but heat comes in because the combustion produce a lot of heat, okay? And then it expand the system, so it does the mechanical work. So in this case, adiabatic process, okay? And then excess heat will be dumped out, and then piston will be pushed back to the original position. So in that case, so in this case, you can see what we talked about last time. So for this cyclic process, so the total work done then will be equal to the area enclosed by this enclosed path. Okay. So QH and then W, the area here, and then the QC comes out. All right. So mathematically, you can write it in this way: work done by the engine equals to the heat it takes in minus the heat, the excess heat it discards. So Q in, we'll write it as Q of H because heat is taking on from a higher reservoir, and then Q out, we'll write it as QC, so that is the lower temperature reservoir. Okay. All right. Now, you cannot, as we mentioned last time, you cannot convert all the heat into work. So this is the second expression that actually we took a look at it first last time. So it's impossible in any system that for heat transfer from reservoir to completely convert it into work in a cyclic process. Okay. All right, so W equal to QH minus QC. So three main components of the heat engine. There should be a hot reservoir, which provides the heat, Q of H, and there's an engine that convert part of the heat into work, W, and then there should be a lower cold reservoir here, okay? All right. The efficiency of the heat engines, so because it converts heat into work, so then it's how much work can be converted over how much heat it takes in. So efficiency of heat engine should be equal to the work done divided by the heat it takes in. And the work done is equal to the heat it takes in minus the heat is discarded. So then you can also do that. So QH will cancel, gives you 1, but this QC also will be divided by QH. So it can also be equal to 1 minus QC over QH, okay? So it depends on what you if you know work and then the heat takes in, you can take this expression. If you just know how much heat it takes in and then how much it discard, then you can use this expression on that expression. But at the end, they will give you the same answer. W is in work and Q is heat, so they have the same dimension. So their units will cancel out. Okay, so efficiency then have no dimension. Let's take a look at example here quickly. It says an engine receives 660 joules of heat from a hot reservoir and gives out 420 joules of heat to a cold reservoir. What are the work done and the efficiency? Okay, so pretty simple. Work done is equal to QH minus QC, and efficiency given the two Qs, you can do 1 minus QH over QC as we done previously. So you can go quickly back over. So this is the equation to use for the efficiency, and here this is the equation to use for the work done given these two. Okay. All right. So I'm going to show you guys the work quickly. Okay. So QH given QH equal to 660 joules, QC equal to 420 joules. Then in A, W should be just equal to QH minus QC. Okay. So that should be this guy minus that guy. So pretty straightforward. It gives 240 joules. Okay, on that one. B, efficiency. Now you have work already as well, so it's either W over QH, or you can do E equal to 1 minus QC over QH. Okay, so that will be the same. I will use this guy. So this is 240 joules over 660 joules. So E then equals to 0.364, or if you want, you can do percentage, 36.4%. Okay, this equation will also gives you the same results as what we have using this equation. Okay, all right. So let's go back to the slides. All right. So we human are always strive for excellence, right? So there's always a desire to bring the efficiency up. Okay, so but according to the second law of thermodynamics, you cannot just convert all the heat into work. Okay, so there's a limit of how much you can convert it. Okay, so it turns out that Carnot engine, which is a type of engine that can do the convert the heat into work most efficiently. So it's determined by the the temperatures of the two reservoirs. Okay, so efficiency equal to work divided by QH, and then it's QH or W minus over QH, QH, W is QH minus QC over QH. So 1 minus QH over QC. And the engines is using the heat air gas as the enclosed system. So it mathematically, again, it's from the PV diagram here, you can see, so QH comes in. So in this case, for the engine, so again, these are the 4 cycles, the gas, it starts from here, you ignite the gas, and then it produces heat, and then it does work, then discard the extra heat, and it goes into the initial state of just gas, and then ignite again, and then the cycle repeats itself. Okay, mathematically, you can see that. So for the best engine you could have, you'll have well insulated. Okay, so during some of the processes here, heat is not escaping. So then from A to B here, this is an adiabatic. This is actually a isothermal process. Okay, because it's well insulated. And adiabatic is the process from here to here, and then back here to here. So all this you can calculate for the isothermal. Work done is nRT ln final volume divided by initial volume that we learned last time. And this is also isothermal process. And then these two are adiabatic process. Okay, so that happens during two of these cycles. Okay, so adiabatic process, that means no heat escaped. So then in this case, you can see the Q is nRTH for the higher temperature, higher reservoir, line of VB over VA. And then here, line for this QC is nRTC line VC over VD. Okay. It can be because these two are adiabatic process. Now, this can be shown in math that VC over VD actually is equal to VB over VA. Okay, so but we need to use a little bit of the calculus knowledge, but it can be proven that these two this over this is equal to this guy over that. Okay, so then we'll just take the result from there. So then QC over QH, then it's basically these divided by that, but law in natural logarithm is the same here and there because the ratios of those VC over VD and VB over VA are the same. So then those will cancel out. Okay, so then QC over QH is just determined by TC and TH. So E equals to 1 minus QC over QH then is equal to 1 minus TC over TH. So this is then the maximum attainable efficiency engine could have, okay, given the temperature of two reservoirs. And no engine can actually exceed or achieve that efficiency. You can go as close as possible, but you will never achieve that in reality, okay? But that's the limit of the engine. Okay, so let's take a look on this example on the Carnot engine efficiency. It says that the engine takes in 2000 joules of heat from a reservoir at 227 degrees Celsius and does some work and discard the rest heat to the reservoir at 770 or 77 degrees Celsius. It gives us two temperatures, okay? They are given in Celsius, so we know that we need to convert them into Kelvins because Celsius is not SI units. So when calculating efficiency, right? For Carnot engine, so let me just switch my camera. Okay. And I'll stop sharing so you can see this better. So TH is given as 227 degrees Celsius. So converting into Kelvin, we do 227 plus 273.15. That gives us about 500.15 Kelvin. Okay. And TC given as 77 also plus 273.15. That will give us about 350.15 Kelvin. So then the Carnot efficiency, see, it's not focusing well. All right, that's better. So for A, Carnot efficiency E sub C is just 1 minus TC over TH from the previous slide. So we plug in numbers right now. Make sure you did the conversion of the two temperatures first. Okay, so that gives you about 0.300, or again, 30%. Okay. Now, because now the second question, if you look at the slide back there, it's asking you how much work is done. Okay. So this is the efficiency. Efficiency can be also defined as, so we talk about two forms of efficiency, right? So W over QH. So if we use this one instead of this one, then we can find out the W here because this is efficiency. Now we have it here. So then W, according to this, is efficiency times QH. Okay, so 0.300 times the 2000, excuse me, joules of energy as is stated in this problem. Okay, so that gives you 600 joules. And in C, it's asking you how much heat is discarded. So that's looking for Q of C. Now we have Q of H, we have W. We can do QH minus W because W is QH minus QC. So QC is QH minus W. 2000 joules minus 600 joules. That gives you 1400 joules. Okay. All right. So go back. All right. Now let's talk about some more applications of thermodynamics in some of the things we use daily, heat pumps and refrigerators. Okay. So now normally for natural process, the heat goes from a hot temperature reservoir to a cold temperature reservoir, right? And in the process, it actually does some work. Now, you can make the heat actually flows from lower reservoir to a higher reservoir. In order to do this, you have to add work into the system. So then it's actually basically the reverse process of the heat engine. Okay, so Heat engine takes heat in from hot reservoir, convert the partially work out mechanical work, and then discard coal heat to the coal reservoir. For the reverse process, in the case of a refrigerator, it takes heat from the coal reservoir, and then with the aid of the electrical work into the refrigerator, it decides excess heat to the outside environment. Okay, so in this process, your coal reservoir is the food or the inside of the refrigerator, and the hot reservoir is the room temperature outside of the refrigerator or the kitchen. Okay, the room temperature of the kitchen in that case. So then, similarly, if we denote heat to the hot reservoir, now use QH in this time again, and then QC is a heat taken from the cold reservoir. So then the same equation will apply. QH will be equal to QC plus W, or in the previous case, we say W equal to QH minus QC, but here it'll be the same thing, okay? But it's just the reverse process. So refrigerator is basically a heat engine, but just running backward. Now, because the refrigerator removes heat from the interior, and at the same time, it requires a certain amount of work. So this amount of work is the amount of work consumed by this process. So we want to know how efficient the refrigerator is, then we'll talk about how much heat it's able to remove with how much work is required. Okay, so similar to efficiency of the engine, we call this as coefficient of performance for the refrigerator. So we use the first letters of the words here, COP, that equals to how much heat it can remove divided by the work. Okay, so again, this will be dimensionless because Q and work have the same units. So normally, the more heat it can remove with certain amount of the work provided, that's the better. So that means the refrigerator is more efficiency. Okay, so next time when you are buying a refrigerator, look at the coefficient of performance. If it's larger, that's better. That means it's more efficient. Okay. All right, let's take a look on this example on the refrigerator. It says a certain refrigerator with a coefficient of performance of 1.75 absorbs this amount of heat, 3.45 times 10 to the fourth joules of heat from the low temperature reservoir during each cycle. How much mechanical work is required to operate the refrigerator for a cycle? And how much heat does the refrigerator discard to the higher temperature reservoir? Okay, so this is again looking for work, and QH here, it gives you QC because this heat is from the lower temperature, and then it gives you COP, coefficient of performance. Okay, so then from the coefficient of performance definition, COP equals to W over QC. We can find W in A, and then once we have W in A, we can find QH in B, which will be then QC plus W. Okay, so again, quickly, let's take a look on this. So this time we are given COP and QC. COP is 1.75, QC is 3.45 times 10 to the fourth joules. In A, we are looking for W. So COP equals to W over QC. Then W is QC times COP. Okay, 3.45 times 10 to the fourth joules times 1.75. Oh, actually, let me see. I don't think I have the right equation. Sorry about it. This is not right. COP is equal to actually QC over W. Okay, so then W will be equal to QC over COP. Okay, so that's the algebra here. So you move the scale to the other side and then move this to the right hand side. Okay. So this will be 3.45 times 10 to the fourth joules over 1.75. Okay, that gives you 1.97 times 10 to the fourth joules for the work needed to operate this refrigerator in one cycle. And for the heat, it will discard to the higher reservoir. That will be QC now plus W, 3.45 10 to the fourth plus 1.97 times 10 to the fourth joules. Okay, so that gives you 5.42 times 10 to the fourth joules of the total heat that will be discarded to the environment. All right, so we'll go back to the slide. Okay, now let's take a look on just kind of expand the refrigerator a little bit bigger to the AC. So AC is essentially a refrigerator, just bigger. So the inside of the house now is the inside of the refrigerator, right? And then outside of the house is now the kitchen in the case, okay? So the cold air will be inside, and then the hot reservoir will be the outside, and it will takes in electrical work or mechanical work in this case. So in that sense, AC and refrigerator are essentially the same thing. All right. So we all know that if you keep the door of refrigerator open, eventually the temperature of the kitchen will go up, right? So it's the same thing here. So all that's because of the because there's extra, so you can take out just QC, but QH is always bigger than QC. So then the temperature will actually become the temperature of the kitchen will actually become warmer. Okay, so that's this statement is about. Lastly, we will take a look at the heat pump. Okay, so heat pump now this is again similar to ACR refrigerator, but we just have the two reservoirs flipped. So in this case, for a heat pump, the outside is the cold reservoir and the inside is the hot reservoir. So you take in certain amount of heat from the outside cold reservoir with the mechanical work. So then you'll be able to supply the heat to the inside of the house to warm up the house. Okay, so pretty much the same thing. And let's say just switch the reservoirs. So then for the coefficient of the performance of a heat pump, then you'll be looking at how much heat it can supply to the house compared to how much work is needed. Okay, so COP for a heat pump then will be QH over W. Okay, work is again QH minus QC. And if this is a ideal heat pump, then this can be written as 1 minus QC over QH times QH or QH times 1 minus TC over TH for ideal engine. So this is like a reverse engine. So in that sense, the same thing, TC over TH is equal to QC over QH. Okay. So coefficient of performance of a heat pump is QH over W. Again, you'll be looking for a higher number of COP, coefficient of performance, for higher performance in this case. All right, so a quick review on what we learned today. We talked about heat engines, the mathematics. So work done is equal to, for the heat engine is equal to heat it takes in minus the heat it discarded. Efficiency is work over QH for heat engine because it does work. So that's 1 minus QC over QH. Carnot engines efficiency, if this is a perfect ideal engine, which does not exist in reality, but that's the higher limit of any engine given on the two reservoirs is 1 minus Tc over Th, okay, determined by the temperatures. We also talk about heat pumps, refrigerated, and ACs. So those are just reverse heat engines with different heat flow from cold reservoir to hot reservoir with the additional help of the work. Okay. All right. So that'll be it for today. I'll see you guys next time.